Hello, everyone. So this is my honor, privilege, and pleasure to introduce HUGO LAROCHELLE to this audience. I would want to say that Hugo is our guest, but I feel bad saying this because I'm a guest to Montreal, and he's actually a Quebecois and Montrealois at this. So I guess the roles are mixed at best. Hugo made his master's and PhD here, then did a postdoc in Toronto. Along that time, he started a startup that was acquired by Twitter, so he worked for Twitter and then decided to move back to Montreal to lead the Google Brain team here. But he still has ties with the academia, supervising students, and actually teaching on YouTube new generations of neural network students. So I watched his classes online, I read his Hugo 2 cents notes on papers. I guess the last one happened like 2 years ago, but they were great, Hugo. So honestly, I don't know how he had time to do all of this and still excel at all of these tasks. So Hugo, thank you for coming and welcome.
Should I use this or that? Oh, so I guess I need to use this mic, yes? You guys hear me okay? Yeah? All right, so thanks for the invitation. I'm really glad to be here. I'm really happy to talk about some of the research I'm excited in. So I don't know whether it's okay to take questions during. Is that fine, or should I wait at the end? Okay. All right. So clarifications, yes. Longer questions in the end. But do ask these clarification questions. Hopefully this is, I don't know to what extent this will be a new topic, but it's definitely one that I'm particularly fascinated and interested in, and it's been the focus of my research in the past year or so and continues to be. So I'm going to talk to you about few-shot learning, or how to generalize from few examples with meta-learning. So the broader context for this research is that I've always been interested in deep learning. My PhD was like at the sort of resurgence of neural nets and the beginning of deep learning. And as we know, we've had a lot of success, but a lot of success has been enabled by the availability of a lot of labeled data for each given task in speech and image recognition and NLP. And obviously collecting all that data is very expensive. And I think the question we need to ask ourselves is whether this is how we think we're going to solve all problems in AI that we think we should be using machine learning for. There used to be a time where we sort of gave up on similar things that required a lot of human labor, like expert systems, where there was a fair amount of like humans putting work into feeding some information to a machine. Now we're doing it in a way that's a bit more flexible by providing labeled examples. But if we have to do that and provide a million examples for each task we want an AI system to solve, I would argue that they're probably not scalable to a fully fledged AI system that can do all of the wonderful things that we're able to do. And I think scientifically that means it's interesting. We probably don't learn all things by practicing it a million times. There are things that we actually learn to do pretty quickly. And so in my whole research agenda across the years, I've been really interested in finding alternative ways of exploiting data from other sources than the task at hand that we want to solve. And there are many ways of doing that. We can do unsupervised learning. We can do multimodal learning, where we have data that comes in multiple modalities. But what I'll talk about today falls in this category with what I call multi-domain data, and specifically transfer learning, where here what we're going to try to do is exploit data from a lot of different but related tasks. So the one picture to keep in mind as I'm presenting this is of this task right here. So this is, we're going to look at I'm going to focus on vision, computer vision, because that's been the task people have looked at for few-shot learning the most. But I think some of the ideas here could translate to speech or to NLP. And actually, I think it's an interesting sort of venue for more research. But here we'll focus on problems where we are given a training set that is very small. So in this case, we only have a single example for a 5-class classification problem. We have this Sunday, this thing, I'm not sure what it is, something, this dog, lion, and a bull. And then what I want is to get a predictor that will be able to classify new test images, such as this lion here and this bull here. And so we want that's often given by Josh Tenenbaum, where he's showing this engine here, which is, and then you need to essentially identify it from one of these images right here. And most people will recognize that this is probably the one that's in the same category as this. And then just in general, we have evidence that from just a single example or a few examples, we become pretty good at recognizing the same visual concept in new contexts. And there's been a fair amount of progress in the past 2, 3, 4 years on machines that are, so machine learning algorithms that are able also to do forms of fast learning of new visual concepts. Here I'm sort of pointing to this paper in Science from Josh Tenenbaum's lab with Brendan Blake and Ruslan Salakudinov, where they showed that they could use human-level generalization on a similar problem of where they were doing character recognition of various types of objects, like this one. The other reason I'm interested in this problem is that, so scientifically there is this gap, and I think in terms of research, fundamental research is really interesting to study, but also if we had systems that were good at this, we could have, these could be very, very useful to really democratize machine learning and make it easy for people to train, for instance, visual classifiers very easily. To illustrate what this would look at, right? So we recorded a little demo using this website that's designed by Google, Teachable Machines, which is meant to show how one can train a classifier using that webcam, a 3-class classifier, where there's going to be the green class, the purple class, and the orange class. I'll just start the video. So I think I will start the video. There you go. So what I'll do here is I'll make up a classification problem. It will be classified between happy faces, yawning, and being scared. So with my acting skills in full display. And you can see once I've collected data by pushing on each button, it's able to pretty accurately recognize these 3 visual concepts. And next I'll ask one of my daughters to try out my classifier that I've trained with a few images. You can see here it's not really working, it's not generalizing really well. It keeps saying that she's scared, essentially, that it's the orange class. Now we'll collect some data for her, so for smiling, yawning, and then being scared. And once I've collected this data, well, the classifier works well now for her by collecting a bit more data, and that's something we're used to. But ideally what we'd like is that if we do this, but not too much, not for too many people, it could actually generalize to a new person, say her sister, who's less shy. And you can see she's smiling and gets the right class, yawning, and then scared. And it works. So you could imagine that if something like this worked, a lot of people could design visual classifiers for any task, and you probably noticed there's no machine learning expertise required. It was really about gathering 18, 22, and 25 examples for these 3 concepts. So I think in terms of technology we could develop, this would be very, very valuable. Now I should say that this is kind of a best case scenario. We actually tried a bunch of other 3 visual concepts, and many of them didn't work. Also, well, my kids are supposed to look like me. They share half my genes, hopefully. And so this is supposed to be somewhat an easier generalization problem. But the fact is this problem is nowhere near to be solved in general, and definitely not to the point of our own ability as people to recognize new concepts. All right. So let's look at this problem a bit more formally. The few-shot learning problem is this problem of trying to design learning algorithms, so that I'm noting A, that will output either good parameters or will explicitly output I say model here, but I should say, I should have fixed this. I'll talk about this model as being a predictor, and I'll use P instead. So designing or obtaining a good learning algorithm that can give us a good predictor for some classification problem. We'll focus on classification. When fed as input, A training set D train with only a few input and target pairs. Okay, and in the few-shot learning setting, we are assuming that L here, the number of labels, is actually really small. And there's been a fair amount of research on trying to do that as well as possible. Hopefully you've I've argued well that there is a big benefit of having systems that can learn from few examples. And more recently, instead of trying to hand design this algorithm, people have looked at whether we can actually learn this learning algorithm. Okay, can we actually backpropagate through some model which will act as a learning algorithm? That is, it will get as input a training set and will produce a predictor that I can now use on new examples. And so this approach has been called meta-learning and learning to learn. And what I'll do today is present you some of my work, but also in general, the various pieces of work that people have looked at to try to learn this learning algorithm, specifically such that it works well for few-shot learning. So let's add a bit more, and again here, should have used P. So let's look a bit more at some notation to try to perhaps better define what I mean by meta-learning. So what is a learning algorithm? Well, a learning algorithm is it's an algorithm and it has an input. And an input of a learning algorithm is normally a training set. Okay, so it's a function that takes in a training set. And what it outputs is, for simplicity, instead of talking about the parameters of a model, we'll just think of it as outputting some predictor, something that can take a new input and make predictions. And we determine that we have a good, successful learning algorithm when it has good performance on a test set. And what we mean by that is that the learning algorithm for that training set gave me a good predictor that makes accurate predictions of the labels of new inputs in some test set. And that's a learning algorithm. Now, what do we mean by a meta-learning algorithm? So we're talking about learning to learn. Well, now, what we're going to try to learn, what we'll be producing using a meta-learning algorithm is a learning algorithm A, okay? And to train that learning algorithm, we will do meta-learning on what I'll call a meta-training set, which will be many examples of training and test set pairs. So the meta-learning algorithm will be iterating on many examples of few-shot learning problems where I have a small training set, and for that training set, I need to produce a good predictor for a corresponding test set for the same task. And so my meta-learning algorithm will train me a good learning algorithm A. And what I want, so much like for a regular learning algorithm, I want good generalization performance on a test set. But for a meta-learning algorithm, we will be interested in what is a good generalization on a meta test set. That is another set of pairs of small training sets and corresponding test sets for new problems that my learning algorithm has never seen before. So that's important. I'm not interested in the performance on the same types of problems that I have trained my learning algorithm. I'm actually interested in the meta-learner, a learning algorithm that actually generalizes to new problems I've never seen before, okay? Because for instance, in that demo that I've done with teachable machines, some other user might come in with their own new problem that isn't the one that I've given a demo for. So I really want to generalize to new problems. And that's what we call learning. So that's why this is a meta-learning procedure. All right, so let's make this more visual. So as I mentioned before, the task that I'm interested in is to design a learning algorithm that can work well in this setting where I have this 5-class classification problem for these 5 concepts. And I want a learning algorithm that can take this training set and give me a good predictor for the labels of the test images. Well, in the meta-learning algorithm, what I'll assume is that I can train my learning algorithm on many other related problems. And those problems, I'll make them be few-shot learning problems because these are the types of problems I want my algorithm to work well. So specifically in meta-learning, we will define a notion of episode, where an episode is a pair of these D-train and D-test sets, okay? So each episode will correspond to a different classification problem with its small training set and its test set. And when I do meta-learning in this episodic framework, what we will normally do is we will do a form of gradient descent by going through a bunch of examples. But now our examples are these episodes, these examples of small shot classification tasks. So specifically, what I will do is I will iterate over all my meta training pairs of D-train and D-test. So I'll take the first episode. I will feed the small training set to my meta learner. So this is my learning algorithm that I will be updating one episode after another. And my meta learner, once I feed it a training set, it gives me a predictor, which I can apply on the inputs of the test set. And then I can measure a loss by comparing the predictions with the labels on these test images. And now in meta learning, we will be trying to find ways of essentially backpropagating the gradient of that loss all the way inside my learning algorithm, so that next time for this episode, it produces a better predictor for the same problem. And the way we will do that is that we will make all of these arrows differentiable, and we will essentially do gradient descent. Okay, so we're sort of embracing this idea in, for instance, deep learning, where we're trying to learn from the raw inputs to the outputs, where here we're doing the same thing, but we're doing it in the space of classification problems. That is, we want to learn in an end-to-end way the process of taking a training set and producing a predictor so we can make predictions on new inputs from that problem. And so meta learning will look something like this. I take one episode, I take the training set, I obtain a predictor that I apply on test examples and compute a loss, and then I will backpropagate into the parameters of my meta learner, my learning algorithm, and then I'll iterate to the next episode, which will be a new classification problem with 5 different classes, so it's a new classification task. I will take in the training set for that task, get a new predictor for that task, and get a loss comparing the labels for the test set of that task, and then backpropagate again and update the parameters inside my meta learner, and do this for all of my episodes in my meta training set. Okay? And here the hope is that if I do this, I'm going to learn a good function A that takes a training set and gives me a predictor that will generalize well to the other problems that are in my meta test set. And crucially, the way we will all set up our experiments is that we will make sure that all of the classification problems that are in my meta training set are entirely different from those that are in my meta test set. So for instance, I mentioned that there was like the class Sunday in my meta test set. In my meta training set, there are no images of Sundays. I'm never going to ask to detect Sundays or classify Sundays or images of Sundays. It will only be in my meta test set. Okay? Yes? Can I have redundant classes in one episode? Is that the question? Oh, okay, yes. So the question is, if I understand correctly, is it possible that I'll have 2 episodes that in the meta training set have the same class? So that is possible, as long as, but what I don't want is a class to be present in the meta training set and in the meta test set. Exactly. But this dog here might be in another episode later. In fact, the way we generate these episodes actually is that we usually take a larger data set like ImageNet, and we will first separate classes into meta training classes and meta testing classes. And then when I generate episodes, I actually do it sequentially. I will stochastically pick a subset of 5 classes from all my meta training classes. I will stochastically pick some images from these meta training classes. I will put some in the training set, some in the test set, and that will be my episode. And I repeat this process. Excellent question. Any other clarifying questions? No? Okay. Let me go forward. So, all right. So this episodic setting of doing meta learning is now quite common in a lot of meta learning methods that you'll read out there. So one thing I do want to clarify is that if you read papers on meta learning, you will often find 2 types of nomenclatures. One of them, which is the one I'll be using, is that when I talk about a training and a test set, I talk about the 2 sets of images within an episode. And then the meta training set and the meta test sets will be sets of episodes that I meta train on or that I evaluate generalization on. Other papers will, instead of talking about training set and test set, they'll say that they'll refer to the training set as the support set in the episode and the query set for the test set instead. In the episode, which allows them to just talk about just training sets of episodes and test sets of episodes. I'm going to try to stick to the notation on the left because I think it's cooler, but that's really the only reason. This one is oftentimes a bit clearer, and sometimes I might refer to support and query set, just so you know, I'm then referring to the training and test sets in the episodes. But I just mentioned it. If you read a paper, some papers will use different notations. Okay, so now I haven't talked about what kind of loss we're optimizing when I said there was a loss that is looking at the predictor's predictions on the test set of an episode. So one way of conceptually thinking of that loss is that what we want to do is, if we assume we have a probabilistic predictor that is giving a distribution over the labels, so for a given image, what is the probability of it being a dog or a cat or a sundae, then one loss I could use is the cross entropy or the negative log probability of the true label of that image in my test set of my episode, given that input. And then conceptually, you can think of it as, well, I'm also conditioning on the training set, because my predictor is a function of the training set for that episode, okay? So the predictor that I obtained was obtained by feeding the training set to the learning algorithm, which gave me a predictor. So another way of conceptually thinking about what is the loss that we're optimizing at every episode is that we're trying to minimize this average negative log probability of the test label in the episode, given the test input and the training set or support set that was provided for that episode. And so now a lot of different meta-learning algorithms and meta-learning models will essentially vary in how they parameterize this P of y prime given x prime and detrain. So in the way they parameterize, how do I make prediction of a test label for a test input, having seen the training set for that problem? And so now what we'll do for the next few minutes is we'll go through various approaches that people have taken for parameterizing this P of y prime given d prime and detrain. How to parameterize this predictor of new labels for new inputs. And conceptually, I like to think of it as there being two types of approaches for defining a meta-learner. There is one which will take inspiration from a known learning algorithm and essentially insert parameters in it that we will be meta-learning. And there's another one which instead will essentially not explicitly take inspiration from our current learning algorithms, but instead just parameterize with some somewhat complicated neural net dysfunction and then learn it on episode and hope that this black box neural net will learn to be a learning algorithm. Will learn to, given a training set, make accurate and good predictions for that problem for new inputs. So we're going to go through various examples of these two families, and we'll start with the first one where we're taking inspiration from a learning algorithm. One of the early examples of meta-learners has been matching networks. Maybe I should move this so you can see who the authors are in the reference. Essentially, in a matching network, the learning algorithm we take inspiration from is, you can think of it as a soft k-nearest neighbor. So in k-nearest neighbor, what do? Given a new test input, we will look at how similar it is to all of the training inputs. And then you can think of a nearest neighbor as having each of these training inputs voting for the label based on how similar they are with the test input, okay? Well, in a matching network, we'll do exactly this. So the prediction of the test label will be an average of the one-hot labels of the input target pairs in my training set, in my support set, weighted by essentially the vote of how much xi is similar to x prime, how much that training input is similar to my test input, x prime. And the way to do this is that they parameterize this similarity as being essentially a softmax applied on the comparison between an embedding of the test input and an embedding of the training input. And so it's a softmax that is, we're going to have the weights or the votes normalized across all training inputs. So if I make the sum of all the votes across my support set or my training set, all the inputs, all those votes sum to 1, okay? And so the way they do that is that they essentially parameterize this embedding function f of x prime and the other embedding function g of xi using a neural net. It might be a convolutional neural net, that would be the simplest thing to do, but in their paper, they actually explore what they call fully conditional embedding, where essentially the embedding of each of these, so in this illustration here, we have a 4-class classification problem. We have a single image for each class. And in this embedding function here, in the fully conditional embedding, we actually make the embedding of each of the image potentially be a function of the other image in the support set or in the training set. And the way they do that is that they put the training images in some random order, and they have a bidirectional LSTM going over each of these images. So now the vector the embedding of any of these images can potentially be influenced by other images in the support set. So I won't say much more. You can look at the paper for more details. But the short story is, a matching network is essentially trying to learn good embedding functions such that a sort of pattern match or a soft k-nearest neighbor classifier works well on these episodes. Another, and possibly one of my favorite approach is what's called a prototypical network. So in a prototypical network, for a given new test input, so I should use prime here, so this is x prime. It comes from the test set of the episode. Instead of comparing that test input with every single training input, the first thing we'll do actually is for each class, we'll extract in a vector representation of that class, which in this paper they refer to as the prototype. And the prototype is just going to be the average of some embedding vector of each of the training inputs from each class. So this is what's illustrated here. If you think of this space as being the embedding space, and where the dots are is essentially the vector embedding for each training input. C1 would be the average of all of these vectors, C2 the average of these vectors, and C3 similarly. And then the way we're going to classify a test input x prime is that we will compare an embedding of x prime with each of the prototypes. So in the paper, the way they describe it is that, again, they'll use a softmax, but now they look at the negative distance instead of a similarity. They think of it in terms of distances. So you look at the negative distance between each prototype and the embedding of my test input. And I pass this through a softmax, so if an input x prime in its embedding space is closer to, say, C2, then the probability assigned by my prototypical network to the class of C2 will be higher because it's closer to that prototype. Okay? And so now when we're doing meta-learning, we're actually going to train the embedding function, f of x. And this embedding function is just going to be some neural net. Oftentimes it's a convolutional neural net that's being used. Okay? Any question about this? You're good? All right. So one way of thinking about a prototypical network, which I find pretty interesting, is that you can, when we're performing this classification here, and if we use as the distance the squared Euclidean distance between f of x prime and the prototype, if you think of it of the prototype as the mean of a Gaussian, and we use the squared Euclidean distance, this form here is essentially the same way you would compute the prediction from a Gaussian classifier. So a classifier where you take for each class the average of the examples of each class, and then the way you classify in a Gaussian classifier is that you do just that. You look at the negative squared Euclidean distance between all of the means of each class and the input, and this tells you what's the class that's most likely. But we're doing that in this embedding space. So we're doing that in this latent space that's learned by my deep neural network. So one way of thinking about, yes? Yeah. Yeah, good question. So the question is, when we're doing meta-learning, what are we updating in this model here, prototypical network? What we're updating are all of the biases and the convolutional weights, all the actual parameters of the neural network, the embedding function. We're not necessarily updating the hyperparameters. if you had a differentiable way of getting a gradient on the number of filters or things like that, you could also do that. You could consider also learning the structure. And some people in the AutoML literature, some people have looked at things like this. But typically, we use a fixed size convolutional neural net. And now what is being learned is essentially what's a good metric space in which to do these comparisons. And that is essentially what is being learned here. And so if we think of doing that comparison with a prototype, if we think of this as essentially applying a Gaussian classifier in that space, you can think of meta-learning here as learning a good metric space such that a Gaussian classifier works well in that space for a bunch of different few-shot learning problems. So this is what meta-learning is doing here effectively. And that perspective is interesting, and other people have sort of added twists to that perspective. There's this paper here where what people are doing is assuming another type of classifier at the top. Instead of assuming that it's a Gaussian classifier, let's assume that's a ridge regression classifier. In this paper, which is currently among the state-of-the-art methods, there it assumes that in the embedded space, you are training in linear SVM. Okay? And in that paper, they show how can you backprop through the training of the linear SVM into the representation, into the neural network that computes that embedding space. So this is an example there of instead of training a good embedding space for a Gaussian classifier in that paper, they're looking at training a good embedding space for a linear SVM. And that has currently pretty much the state-of-the-art results, or some of the most impressive results reported. Okay, so that's another sort of way of thinking of it, where we're gonna take inspiration from a known learning algorithm, but the thing that we will be learning is the embedding space in which that learning algorithm is operating. And we'll learn it such that it yields good generalization, good performance for few-shot learning specifically, because we're training on episodes of few-shot learning problems. Another sort of interesting twist on this idea is to say that this representation network, so this comes from this paper, Tadam, from Element AI. This network here, which is the one that embeds each training inputs into a latent space, right now it's fixed. No matter what, we are training it during meta-learning, but for each episode, it's always the same one, the same network. Another approach is to say, well, actually, let's first process all of the training set, and let's have that training set essentially adjust even the representation itself, so that the representation is also a function of the support set or the training set in the episode. So I don't have a whole lot of time, so I'll just refer to that paper if you want to look at it. But another sort of dimension of exploration in that space of ideas is to say, let's also make the embedding space be a function of the training set. And here they use ideas based on film feature-wise linear modulation, which is one way of conditioning and embedding or representation on some set, on some additional information. Another approach to this is to actually use, again, taking inspiration from a known learning algorithm, is to use perhaps the most popular learning algorithm that we always use, which is gradient descent. Most of our machine learning right now, especially in deep learning, is essentially based on I have some predictor like a convolutional classifier, and then I do gradient descent on it on mini batches from my training set. And this is represented by this equation. I take my current parameters of my predictor, and I do a gradient descent of my loss with respect to my parameters in the opposite direction of that gradient with some learning rate. So in some work that we did in 2017, we were thinking, okay, how can we use that as inspiration for how to do a meta-learner? And this might not look like something we can use, but there are other types of models that kind of look like this, kind of take the form of this equation that we are quite used to doing backpropagation through. For instance, in an LSTM, if you're familiar with LSTMs, we usually have this cell state, and the cell state is essentially the previous cell state at the previous iteration multiplied by some forget gate plus a cell state update multiplied by some what we call an input gate. And now if you replace the cell state by parameters of a model And then if you make the forget gate equals to 1, and then if you consider that the cell state update is actually the gradient of some loss with respect to the predictor parameter, and now you make the input gate be the negative learning rate, you essentially have exactly the same equation. So what this is suggesting is that maybe we can actually backpropagate through a gradient descent procedure. Maybe we could even have a recurrent neural net actually produce the learning rates. Instead of using a fixed learning rate, we would have a recurrent neural net that for every parameter at every gradient descent step tells you how far you want to go in the direction of the gradient. We could even still keep the forget gate, which would correspond to shrinking the current parameters of my convolutional neural net closer to 0. So it kind of potentially act as a regularizer. And that's essentially what we did in this work. We essentially had a recurrent neural network drive the gradient descent procedure when we're training a convolutional neural net on my small training set in an episode. So I'll show visually what this looks like. So what this means is that for a given episode, so for a given pair of D-train and D-test, what I would do is that I would start from some initial values of my convolutional classifier. So I'm assuming that my predictor takes the form of a convnet that has some softmax output weights. And so I start from these weights, and I take my training set and its labels, and then I look at what is the gradient of the parameters of my predictor, my convnet, with respect to that loss for that mini batch in my training set or support set. And then I feed that to my LSTM, which will now give me learning rates so that I can get an updated set of parameters for my predictor, my convnet. And then my convnet is again evaluated against the training set, gives me new gradients for these parameters, which I can pass to my meta learner LSTM, which is producing the next iterate of my gradient descent procedure. And then I do this for some fixed number of steps, capital T, which in practice is never much more than 15 actually, is often very small. It's computationally more useful, but also remember that D-train is small, so if we do too many gradient descent steps, we're most likely overfit on the training set. So actually here it's kind of convenient because a few steps of gradient descent is probably the right thing to do. So then that gives me the parameters of my convnet after T gradient descent steps of my support set or my training set in my episode. And now I can look at my convnet, how good is it at predicting the labels of my inputs in D-test. And then when I train, I'm going to, or when I do meta training, I'm going to backpropagate all the way through this procedure, this gradient descent procedure. So I'm going to update the parameters of my LSTM, which is driving what learning rates I'm using at every time step. And another thing we're actually going to update is what was the initial value of the parameters. So my convolutional classifier, at what weights do I start this short gradient descent inner loop in my episode? So I'm going to train a good initialization as well as a network that gives me a good schedule of learning rates such that on small training set problems, I get convolutional neural nets that generalize well to new inputs. And I'm going to do that in an end-to-end way by going over all of my episodes, doing this inner loop gradient descent, backpropagating through it to learn a good initialization and a good LSTM, and then iterate like this. And actually essentially, most of the transfer learning that's going to happen, most of what's going to be learned in practice is in the initialization. So intuitively, what we think it ends up learning is a good initial representation of most images such that you can fine-tune it just a little bit so that it works well for a new few-shot learning problem. Okay? And notice that it's kind of similar also to how we do transfer learning for many problems. It's quite common to pre-train, say in computer vision, to pre-train on ImageNet and then do a bit of fine-tuning on my other data set with a few images. Well, here you can think of this approach as trying to learn in an end-to-end way that procedure of having an initialization that works well for a little bit of fine-tuning. And I will say that this was our initial work. Now, not so long after publishing this work, Chelsea Finn from Berkeley proposed a much simpler version of that, MAML, for model-agnostic meta-learning, where essentially we're just throwing away the LSTM that is essentially controlling the schedule of learning rates. And all we're going to do is learn the initialization and assume we're doing a fixed learning rate gradient descent step on the training set for every episode. And in fact, a lot of the literature you'll find has shown that if you do a single step of gradient descent, so if you start for your learn initialization and then do just a single gradient descent step, you actually tend to get surprisingly good performance. So in other words, just doing one step of gradient descent on my training set, I'll learn initialization so that even if I do just this one step fitting, I still get good performance on new images of that same problem. Now in practice, sometimes people use more, but what's kind of surprising is that one gradient descent step is sufficient, and they have even derived some theory that shows that this type of parameterization of a meta learner can potentially approximate any form of function that is making predictions of new targets given new inputs and a training set. There's a universal approximation theorem that they derived for a procedure like this, which you can find online. I won't go through. But I mention it because you would think that this would not be sufficient to fit any training set. But thanks to meta learning, because you're really training that initialization such that this works well, it actually is able to solve a surprising number of problems. Any question about this general approach? No question? Maybe one? I'm sure there's one. There's got to be one. No? Should I move forward? All right, okay. Maybe in the end. So if now this procedure of backpropagating through a fine-tuning procedure is sometimes in practice not super easy to make work. I would encourage you to look at this paper, How to Train Your Mammal. This is an iClear paper. And they've explored various variation around that theme of training initialization followed by a few gradient descent steps. There's you can see that like essentially this learning curve here is what you can get with regular mammal. And then with various tricks, they're able to stabilize the learning. And for more details on that, I encourage you to go look at that paper. All right, and so that's one approach. We've taken direct inspiration from known learning algorithms. And I'll quickly go over another approach, which is to just give up trying to take inspiration from known algorithms and actually just derive some black box neural net that can take a training set as input, a new test input, and make prediction of labels. So one way of doing this is to think of the meta learning problem. So for a given episode, to convert it into a sequential classification problem, where the sequence of inputs is going to be, I'm going to provide it in an episode, all of the training inputs at a given, so this is the 10th training input in my episode. And then I'm also going to provide it what is the label of the previous input. So that's the input sequence. And the output sequence is going to be, so for time step t, I'm going to predict the label of the input xt. Okay? So out of curiosity, can anyone guess why here I should not provide yt? I should not provide the label of xt. It would just copy, right? It would learn to ignore the input, and it would just copy and pass over yt. But of course, we wanted to not ignore the input because we wanted to classify new inputs. And now, so that's why we don't provide yt, but can anyone guess why we need to provide yt minus 1 as opposed to no y's? So what would happen if there were no y's here? Right. So here, if we provide no y's, then this might be an image of, I don't know, a Sunday, and then y is going to be a one-hot encoding of the labels. Now Sunday, that might be the first class, that might be the second class, the third class. You actually don't know. For any episode, sometimes Sunday is going to be the third class, sometimes going to be the first one. So if you don't tell it what is the class of each input, then there's no way that it can determine if there's a new input to which class it corresponds to. So this is sort of, it's as if, what if you were training a neural net but without labels? You wouldn't be doing supervised learning, you'd be doing unsupervised learning. But here we want to do supervised learning on a small training set for every episode. So essentially now the neural net here I'm not really specifying what is in this black box, but this sequential neural net will need to learn to bind this input with the following label such that next time, if it finds a similar input to this one, well, maybe it produces or it outputs or increases the probability of the same label that was shown at the next time step. So you can see this is actually, this is sort of allowing to do sequential prediction in such a way that the best solution is to do a really excellent learning algorithm. However, it requires some pretty complicated mechanics inside that black box to be able to do this binding of one input with the following time steps target. But people have designed neural nets for doing that. An early paper on this was this memory augmented neural net from DeepMind, where they use a neural Turing machine to essentially have this memory that's being updated with some read and write procedures that are differentiable. I won't go into this because this is not a method that's used a whole lot today. And in fact, this problem of learning to bind the next time steps label with the current input is so complicated that people have instead started using another approach. So converting the problem or using different types of derived black box. Another approach is to just say, actually, I'm going to align the inputs with the labels, but the way I'm going to define the loss is that I'm only going to predict the label of the last input, and I won't provide it at all in the input. So now we have axis-aligned inputs and targets. And then in my black box, I just define some neural net that can take a sequence and can produce a softmax output. And the softmax output will be compared with the label of the last element of my sequence. And here, what's nice is that this is simplifying much more the problem. We can leverage things that work well for sequences in general, like dilated convolutional layers, attentional layers, like in transformer networks. And so this method is SNAIL, so S-N-A-I-L. This is a trick if you're looking for an acronym. We can do that now. Just pick random letters in between words. And this actually, it works surprisingly well. Even though there's nothing that really compels the neural net to learn to be a learning algorithm, because we train it on episodes, because we train it on examples where I'm going to give you a small training set, I'm going to give you a test input, and now predict me the label of that test input, it actually is able to learn to generalize to new training sets and new test inputs. All right, so now I haven't presented any results, and I'm sort of tempted not to. I will say quickly that in practice, in papers that you'll read out, a benchmark that's used a lot is this mini ImageNet, which is taking only 100 classes from the full ImageNet paper, data set. It's splitting them into 64 for meta training, and then 16 for meta validation and 20 for meta testing. And then essentially that's how you define the benchmark. So you meta train on 64 training classes, but then your generalization is evaluate on new 20 test classes. And then the way you create episode is you take a subset of these classes, take a subset of the images from these classes, and that gives you an episode. You evaluate the performance, and then you do that multiple times. And initially, people have looked at comparing with just a general sort of embedding learning method where you would, in a supervised way, learn to do 64-way classification on the training set images, and then that give with a regular classifier, and then use the hidden layer as either an embedding space to do k-nearest neighbor on the test classes, where you're given a few examples of the test classes, and then you're doing k-nearest neighbor, or of doing this sort of pre-training on the data from the training images, and then fine-tuning within each episode on the support set of each episode. This is the baseline fine-tune, the baseline nearest neighbor. And people have shown initially that doing this meta-learning method, training on episode, is actually providing for better results. And then later on, here now I'm showing prototypical network, mammal, and snail. The results are honestly sort of somewhat comparable. All of these methods on that benchmark are right now kind of getting about the same numbers, and oftentimes, some of the differences could also be due to other variations in the experimentation protocol or the size of the neural net or things like this. So I don't want to emphasize too much on what methods work well. What I will say is that prototypical network, if you want to start with one method, that is probably the easier to train, the one that trains fastest, and perhaps the one you want to start first. All right, And so I just want to end my talk with sort of talking a little bit about what I think is interesting future research and give you examples of people that have taken few-shot learning and meta-learning research in interesting directions. And there's essentially two categories. There is one which is to go beyond doing just classification and looking at other types of few-shot learning prediction. And the other one that I've been mostly working on is trying to go beyond only evaluating ourselves on this mini ImageNet dataset, which is very simple, and actually starting to design more realistic benchmarks that hopefully will bring us closer to this real use case scenario that I showed with teachable machines, for instance. So a few variations. Actually, I think I'll just skip this one because I'm almost out of time, but I'll just mention that we have looked at, for instance, how to do meta-learning in the setting of semi-supervised learning. That is a setting where, in addition of a training or a support set in an episode with labels, you also have some additional images that are not labeled. And we can use this episodic framework and define meta-learners that are trained for this specific setting to leverage the unlabeled examples better than if you did sort of various baseline things. Another interesting one that I like is this one here, where you can try to learn a neural net to do data augmentation. So you can think of data augmentation as really just this function that takes in some real image, it takes in some random variables, and then these are combined to produce a new image of that image, a new variation of that image, but it is meant to preserve the same class. Now, we have data augmentation functions that we know preserve the same class, like translations and rotations. In this work, they just think, okay, let's actually just force whatever images it produces to be of the same class and feed that to my meta learner, like a prototypical network. And let's meta learn it such that this network G is forced to produce images that help with generalization. So in other words, train that function such that it does improve the performance on new images when you assume that what this function is producing are other variations of the same concept. So you can look at this paper here. I think it's CVPR 2018. Instead of doing classification, you can look at doing few-shot density estimation. So now the predictor is a density estimate. It's something that gives me how likely this particular input is. So the way you create episode is that, so this would be one episode, this is another one, this is another one. So in one episode, you would generate all, you would provide all images of the same concept. So these, I think, are characters from the Omniglot dataset. So there's from some alphabet, but there's the same letter. And then you would provide, so this would be the training set or the support set. And these are actually samples that are produced. But for training it, you would provide as the test set another set of different characters from the same class, from the same concept. And it defines some meta learner that would allow you to condition on this training set to obtain a new generative model of other images from the same concept. And it's trained in these episodes to do exactly that. And they later built on this work to do few-shot text-to-speech synthesis, where now the episodes are, for a given episode, I'm going to have a single speaker, I'm going to have a few utterances from the same speaker. And now what I'm going to do is that, or what I want is, I want to be able to invoke an embedding for that speaker and condition a wavenet, which can produce speech. That's also going to be conditioned on what text should be uttered, and also the fundamental frequency of the signal. And so in this setting, they're training both the wavenet and a set of embeddings, one for each speaker. And then the way they do few-shot speech synthesis for a new speaker is that for that speaker, you collect a few utterances. You will then train only the embedding such that the wavenet assigns high probability to those utterances for that speaker. So we'll essentially infer an embedding for this new speaker. And then you can now change what is the linguistic text and have that person say anything. They had like some pretty surprisingly good result at essentially from a few utterances of one person being able to generate new sequences of speech of other text. If you want to check this out, this is from iClear 2019, just this year. There are also work that is looking at image segmentation, where the support set now is providing us with an image, as well as key points of which pixels should belong to the foreground and which pixels should belong to the background, which are the positive pixels and the negative pixels. And what you're going to train is a function that takes that support set and now produces a network that can do segmentation on a new image. And now you actually wanted to produce the segmentation of the whole thing. So in this case, the positive foreground pixels were those corresponding to that dog, and the background were anything else. And now in this new image, this is meant to signal that for this new image, you segment out a similar dog. And you can see that indeed, for this image, it produced mostly foreground where there is this white dog right here. And so in that paper, they figured out a way of using fully segmented data to generate these episodes such that when you do meta-learning, you're going to meta-learn a segmentation method that can take in this very sparse segmentation information and produce a segmentation method that works well on new images. So this is from Kate Rakely from Berkeley also. You can go check this out. And so I think one direction is definitely sort of looking at other non-classification problems, and you've seen a variety of more structured prediction or density estimation problem, or also just thinking about what would be information I would want a learner to be conditioned on that isn't just fully supervised data. This is what this example was. In this case, we're really providing very weak supervision for a new problem, and then you train a meta-learner to be good at doing that. And then the other direction, I think, and something we really need to be mindful of when we do research as meta-learning, is to think about how do we construct our meta-training sets. Because the meta-training sets is meant to represent the type of problems that our system will be confronted with when it needs to generalize, okay? And if we don't do this right, then it might not generalize well to new problems. So in mini-ImageNet, where we're actually always assuming that there's the same number of classes and the same number of images per class. And that's really unrealistic. We do expect that if there's a new user that is collecting images like I was doing with Teachable Machine, there's going to be a variety of a variable number of images per class. And also in Teachable Machine, it was fixed to be 3, but some user might actually want 4 or 5. And so one piece of work that we did with my intern, Eleni Triantafilou, in this paper called Metadataset was to design what we think is the sort of next generation of benchmark for doing few-shot learning for classification. The paper is online, and the code for the data set is also available. And here in this setting, what we decided to do is that we're going to literally have a data set of data sets. These episodes are meant to represent different classification problems, which each have their own data set. Well, there are multiple data sets that are available out there. So why not group them all together and use that to structure our metadata set benchmark? So in metadata set, we actually joined together these 8 sources of image data. So we put ImageNet and Omniglot, these images of characters for various alphabets together, which make for very different classification problems, but that we think should share some amount of structure between them. There's an aircraft data set, birds, describable texture, quick draw, which are other type of symbols being drawn, fungi, because why not, VGG flowers, or various types of flowers, traffic signs, and then MS Coco, which has other types of visual concepts. And because traffic signs and MS Coco don't actually have a lot of classes, we actually only use them to evaluate generalization. So when we do meta training, we will never train on any images nor classes coming from these two. For the other data sets, the way we set up training is that we still do this separation between meta training classes and meta testing classes. And then we only train on the meta training classes, but evaluate generalization on meta test classes from the same data set. So they're potentially a bit more closer conceptually, but they're still a stronger form of generalization than we're used to in regular supervised learning. And when we generate the episode for a given episode, we'll have a variable number of classes, of images per class, and even they're not necessarily going to be balanced. And in the paper, another thing that we did is that we evaluated matching networks, prototypical network, and mammal. I sort of consider these as being kind of the state-of-the-art methods, and there are variations over these that are somewhat better. But those are the basic sort of building block and basic baselines people should do. And one thing that we did is that we proposed a combination of prototypical network and mammal. Now, realizing I'm going a bit over time, hopefully that's not too bad, or should I really try to wrap up quickly? I don't have that many more slides, but yeah, okay, all right, I'll try to wrap up. So essentially, the TLDR for proto-mammal is that you can think of the prototypes that are being produced as being the output weights of a predictor, and then you can use that as the initialization for your convolutional neural network that you're applying. And so we essentially have a first phase of prototype extraction followed by a few inner loop gradient descent step on the prototypes and the weights of the neural net. And that turns out to work better. And so you can look at the paper for results, but essentially that combination of prototypical network and mammal actually gives the best performance, and it does better than a k-nearest neighbor baseline or a fine-tuning baseline. And it's the case when we only train on data just from ImageNet, or we train on data coming from all data set sources. And but however, one interesting future direction for research is that what we find is sometimes, if we look at the difference of the performance, whether we train on just ImageNet classes or all classes from all prototypes, we actually find that sometimes it's better to train on all classes from all data sets. Sometimes it's actually better to train only on the classes of ImageNet. And what this suggests is that current methods are not particularly good at handling sort of heterogeneous sources of episodes or few-shot learning problems for meta-training. And so that, I think, is an interesting future direction of research, to have more robust methods that can train a much more complex set of training problems. All right, I'll just skip these, which are essentially just showing that training on more shots and more examples works well. And I suggest you go look at the paper for the various conclusions. I encourage you, if you want to do meta-learning research for classification, to consider using metadata set. I'm hoping that this will be a good next step for our research. So yeah, so that's sort of the message I wanted to send, that there are many problems still yet to investigate for meta-learning. And however, we also have discovered many interesting ideas that are useful in the context of doing research in transfer learning in general. But I think there's still a lot to do, obviously, either in terms of addressing more complicated problems than just supervised classification, like I mentioned, or actually doing supervised classification, but being a bit more realistic in our scenario. So actually starting to get closer to a setting that might look more like the teachable machine demo that I showed before. All right, with that, thank you all.
So thank you for this great inspiring lectures. I will give the microphone here back where it belongs, so that you can ask questions.
You can also repeat the question if you don't want to use the mic.
So are there?
There's one there. Yeah, sure, absolutely. Yeah. Yes.
Thank you. Can you give an intuition on why just one step of gradient descent worked and was enough?
So, not really is the question. I thought it was a surprising result, the universal approximation result for one step of gradient descent. The main intuition that I would give is that because we're looking at few-shot learning, which means that the training set in an episode is very small, it's not too hard to imagine that we will very quickly or potentially overfit on that training set. Now, one step of gradient descent is an extreme of what you could do. And I think ultimately the reason it still works is that you are training the initialization such that that one step of gradient descent is very effective, is as effective as possible. So that is, if you just pre-train an initialization without taking that into account, and then just the one step of gradient descent, I wouldn't expect that to work well. But because you've trained jointly, or you've trained that initialization to work well in the context of one step of gradient descent, I think this is why we're still getting a lot of mileage out of this. Now that said, I would say like in practice, it's a good sort of first thing to try. I've seen variations where people would train with one step of gradient descent, but then they would treat that as a hyperparameter where at test time, or like on the validation set, they would, after they've trained, try 2, 3, or 4, and then pick whatever actually works best after meta training, and then just use that when evaluating on the test set. And that might give you a bit better results. But there might be other things which are, it's just like, it's faster to train because you're doing one step, so the inner loop is much faster. For each episode, the processing time is much faster. I think that's part of the reason that empirically we have better success. And we found that objective to be a bit hard to optimize. You've seen that wiggly curve where it was pretty unstable in terms of the performance. And while there are tricks, and maybe with these tricks now, actually doing more steps is just empirically better. One step is just like practically very convenient. That's a good question.
There is a question here, but I would like to ask the other people that don't ask questions to essentially go out of your place and maybe come closer to here, that it will be faster.
Okay, thanks for the talk. So I have a question about MAML.
Yeah.
So you showed when you're comparing about ImageNet, like these methods kind of have the similar performance, but on the metadata set, MAML perform much worse than the others. Can you expand a little bit more about the reasons you guys think that happened?
So wait, so on the, are you referring to this table here?
Yes.
Or? Okay. So you're saying that when we only train an ImageNet.
Oh, no, talking about just the mini ImageNet, not comparing about.
Oh, okay, sorry.
Because there you see that the performance of MAML and the other methods are similar, but then.
Okay, but it was much worse. Yeah, that's a good question. So, and honestly, like we were really wondering why we weren't getting those good results, and I think it's largely a reflection of the fact that MAML, like basic MAML, is a bit more unstable and harder to train. I think if we had used some of the tricks that are in the how to train your MAML, probably would have obtained better results. But we use the same code base for proto-MAML and MAML. And the only thing that changes is essentially how we initialize the output weights of the predictor, where proto-MAML is using prototypes. And that makes a huge difference. So I think part of it might just be that proto-MAML is just bringing more stability to training. And I guess the short answer is that I think it's just a harder method to make work. I should say that while we do gradient descent through that gradient descent procedure, the method that we applied here, when we do MAML, we actually do a version that we call first order MAML. First order MAML is the fact that we don't actually backpropagate through the gradients in the inner loop. So the gradients themselves are also a function of the initialization. So that would you need gradients of gradients. That brings more, it's more computationally expensive. It also requires more memory to do this. And so oftentimes in practice, people will use the first order version of MAML, which does a stop gradient on that gradient. It doesn't, you ignore those gradients essentially. And it's possible if we had done the second order, which we found to be too slow essentially in practice, it's possible we would have had better results. Oh yeah.
Any more questions? So maybe I'll ask the last one.
Sure.
So you started that we shouldn't have many labels. You want to have few labels. Do you think that the unsupervised learning thing is still a thing, or it's like even a small amount of labels trumps the unsupervised, and you should do whatever you can with say 20 or 10 labels per class, but 0 is like essentially a quantum leap.
So part of the reason that I've moved to few-shot learning, there's a few reasons. One of them is really, I think, well, again, there's this gap between our abilities and the ability of machines. Also, I think practically, oftentimes people are faced with problems where they would want to provide just a few examples. And also, these methods of meta-learning for few-shot learning are meant to be easy to use. Like once you've trained your system, anyone can use it. All they need to do is provide training sets. And they can even do it interactively. They can, start with a few labels, look at the mistakes it's making, and then label these and put them back in and immediately get a model. And what I found is that this is, a few labels gives you a lot of information compared to unlabeled examples. And I think for a lot of problems, unless you figure out what are the right self-supervised or unsupervised objective, it is quite easy to not have the right objective for that problem. So I personally think that the problem of, so being in a setting where you assume that at test time, you're going to be given a few examples for that problem is a good setting, because most of the time, that's really the situation that people will be faced, at least in practice. However, I will say that I think that the few shot learning provides for an interesting benchmark for unsupervised learning methods. So one thing I didn't talk about too much is that when we do training, so these, like for instance, mammal, we need to initialize the initialization. We need to find initial parameters of the predictor that we're going to be training to be a good starting point for a few gradient descent steps. In practice, we can initialize this randomly like we normally do. You can also pre-train it in some way. And some people, what I've done is that they first pre-trained an initialization, kind of like in the baseline fine-tune, by doing regular 64-way classification, and then you initialize mammal with this, and then you fine-tune mammal in this way. And that oftentimes actually gives better results. On metadata set, this is actually what worked best. I think it would be quite interesting to see whether there are unsupervised learning methods to do that pre-training that work well in that scenario, and evaluating methods in that scenario. And there's potentially a reason to think this might be better than even supervised pre-training, because here we're looking at generalization for new examples of entirely different classes. And so it's not impossible that the advantage of unsupervised pre-training, which can cover data that's much broader and potentially actually cover the input space of the classes that you'll be presented with at meta test time, then you might actually start seeing some benefit from unsupervised pre-training. And so I haven't seen people use that as the evaluation protocol for unsupervised training of representations, but I think it would be an interesting one. And it might be one where we actually start seeing a benefit for actually doing some forms of unsupervised learning.
Would you assume at a realistic scenario that you actually have the unsupervised data for the end, for the target problem? Or
so
is it somewhat unrealistic?
I think what's realistic is to, this meta learning scenario, I think, is realistic in the sense that it doesn't assume that during meta training, it has seen data like the data we'll see at test time, at meta test time, I should say. However, it is assuming, or the setup is such that when we do the evaluation at meta test time, we do provide for each episode a few examples of those problems. And that, I think, is realistic, or it's definitely not asking a whole lot of work from the user. And I think if that scenario worked really well, and I think that's it's a hard problem, it's still much easier than just assuming you can learn the best representation that will work from scratch for any problem. I think that's putting the bar a bit lower in terms of what needs to be achieved, but it would still be transformative. I think if we had methods that worked really well in that scenario, this would broaden the use cases of machine learning methods much more than what it is right now.
Okay, thank you very much. And
thank you.